Hello everyone. Today we are back again here with another session of AI Research Paper Reading Club. And after many delays, not many but few delays, we finally have Ketan today to talk about ROS LLM. Ketan is a robotics engineer who frequently gives talk about robotics, integrating LLMs and robots, and all the Gen AI part and also the robotic part. So today he's a great combination for people interested in robotics and Gen AI as well. You guys will get to see the aspects of how we integrate some software with hardware using frameworks like ROS, that is Robot Operating System. So let's directly get Ketan here on the stage.
Hi Pranav, how are you doing today?
I'm fine. How are you?
I'm also doing good. So thank you for the introduction. So yeah, as you talk about ROS LLM, the topics actually integrates AI and robotics together. So we
Yeah,
can
Ketan.
start over with the topics.
Yes, you can start.
Yeah, good. So let me just share my screen over there. I hope my screen is visible. So, hello guys, myself Ketan Thorat. I'm a robotics engineer, founder of Robotics Innovations, where we actually try to develop and do R&D stuff over the development of robotics. So, been a while, I was a ROS developer since I have been learning ROS and integrating AI. So, yep, this is all about me. So today we are going to talk about ROS-LLM, a ROS framework for embodied AI with task feedback and structured reasoning. So what's the motivation behind learning LLM and ROS as a robotics? And it's quite surprising that anyone is actually talking about this. But yeah, there is a lot of developments going on onto this where we actually try to learn more about how we can integrate model deployment about into an system which is actually working over there. For now reason, if we talk about the background and motivation, so I have my notes with me. So robot development traditionally depends on expert engineers who manually design, integrate and deploy robots behavior using frameworks like robot operating system. For now, in current days, we have robotic systems which are actually deployed on ROS, but the process is manual. We need to add some AI which will actually redeploy it, and we will be giving it the prompt, and it will actually do all of the tasks which we don't want it to do. Suppose if we wanted, there is a robot, 6 degree of freedom of robot, which is actually cobot. We can talk about cobot. If it is actually moving over anywhere, and I want to grab a thing, if I want to grab, suppose a cup, if we talk about a cup, and I wanted to place over it, so we will be giving it an action, we will be coding over there, and again, after the programming, once that is done, we will do all of the random stuff, and the robot will keep the cup as we want it to do. Now this can be done through lead programming as well, but since again, there is a expert engineer who is all doing this all at the background. First he will do the programming, and then repetitive actions will be done. So in this, there is a lot of development going on where we can, robots are being trained by lead programming through imitation learning. We will also talk about what is imitation learning, and resources that this is actually redeployed in Singapore as well. Previous week I was in Singapore for in ROS conference, where we actually gotten good resources about the same, and the deployments of the robot. I will also share my screen, show you how that imitation learning goes on this. And so, yep, in this cases, every new behavior requires manual reprogramming. As I said, you again, robot cannot easily adapt to natural human instructions. There are some kinematics behind it, if we talk about, and which is required to be done with our physical AI. I mean, physical actions. So not and every actions can be carried over by a human itself. We need our system to be over there, if we talk about. And The paper actually says again, non-expert users such as operators and consumers cannot directly instruct or modify robot behavior. So, yep, that are the cases we are going to learn about today. So, this paper has some good, what we say, structure, introduction, problems, formulation, the ROS LLM framework, experiments, the experiment which have they done through the 6 degree of freedom UR5 arm robot, and again discussions, related works, use cases, and conclusions. So, starting about introduction, I have actually already told you that how this works. Over there, we can have this same, and yeah, there is a lot of, as we discuss about there. Yeah, here again, reinforced learning is used. So let's jump into the right part over there. Problem identification. Yep. So as per we discussed, what's there is a gap. There is a gap between how humans naturally communicate through tasks, through language, and again how robots are programmed through structured codes. So when we talk about this stuff, like and human integration, and again a communication which is required by the robot, which needs to be do it, like the robot which is going to do, and the one which has been taught by human. So we need to identify these gaps. So there we have a good formula structure over there. We are not going to discuss over there, it will take a lot of time. But yeah, I'm going to discuss about the techniques which has been implemented over there. So yeah, what kind of problem statements we are discovered is about manual action sequence, and again let me go through it. Yeah, so extensive testing and deployments by robotics engineer. In the robotics, when we talk about, it takes a lot of time in imitation learning. I think previously when I was in Roscon, there was a robot called by robotics, and in that robot they have actually trained that robot to pick and place it from one like a can, and place it. It take around 60 hours of training, which is too much for gathering the data. And talking about this is what this paper talks about. It's an actually old paper, but giving about an action what it does. So yeah. So as we discuss about the problem statement as well, we will be moving towards how this ROS LLM frameworks works. So in this, we have in both industrial and research settings, the development of robotic tasks often involves breaking down complex behavior, blah blah blah. So yep. So this is the diagram over here, that how it works, and giving it a prompt, everything will be done by the model which is present over in the controller. And yeah, so, what is the research gap and objective behind this? LLMs can understand reason over human instructions. So that's a pretty obvious statement we talk about, that in AI, that the boom of LLMs are too much quite crazy, and ROS can execute low-level robot actions. So to deploy actions, we'll be using ROS, and to work understand what the prompt we have given, that LLM will provide it like a roadmap to the robot how it should deploy. So it's a huge complex if we talk about to do in this stuff, but it's still under the development. But it's good for our understanding that what kind of development has been going on. So hence, the objective of this work becomes to develop a framework that allows non-experts as a operator to initially program robot using natural language by leveraging using the ROS. So, while combining this together, we ROS is a good platform for us to understand how robots will be communicating with this like with the robot, and LLMs will be the one who will be actually giving this decision. Where I think there was a good flow chart over here. No, this is experiment one. Yeah, I think this one will look like what exactly a robot should have a deployment. So here if we talk about expert and non-expert, expert actually does good research about the program. Like it's if we talk about, there is a robotics engineer sitting besides me, and he wants to deploy some of the projects, correct? And if he wants to pick up the cup and place it, what he will do, he will bring the robot down and again pick it up, and again it will move around. He will find the coordinates of it and deploy it. So that's how an robotics like expert actually work about this. So this is a short description about this what we talk about, flowchart, and then non-expert, like if we talk about non-expert, what he will do, he will actually try to understand over it with imitation learning. Now, what is imitation learning? Imitation learning is something which we can actually deploy the robot. We can teach the robot how you should actually pick and place, which is comes under the lead programming. Now you might talk about what is a lead programming. Lead programming is something which you need to basically, it's simple as what we had talk about imitation learning. It's like just there will be two robots in kind of one will be about the human will be doing the action, and second one will be the same, where the robots deploy our actions to do the stuff. So talking about it, let me have like share you for about what exactly it does. Imitation learning, just search it on Yahoo. I'm sharing over the screen so you can understand in better way what imitation learning does. Okay, so let me share my screen over there. um, Yeah. So this is how imitation learning with ROS2 begins. It's like the same procedures are being followed up. There is this one, and again, I think the one which actually is done by the human itself. Um, okay, the basic fundology is that only the robot is actually picking up it by it is actually let's simplify it in easiest way. Suppose there is a my hand over there, I will pick it up. Same action has been performed by this robot over there by this. So the lead has been actually sorry, this will be over there. So the robot which we have in this side, now this is not a robot, this is a lead which we practice for the robot. The same actions will be performed as we do it. So that's how it works. So imitation learning is simply over there, and to actually configure it with imitation learning, we have behavior tree as well, where actually it was been described by the robot or not by the expert who writes the code in format and the way it gets to the development. So this is how what is a behavior tree and imitation learning. Imitation learning goes very easy for operator to use the robot by the lead programming, and behavior trace by simply using our logic program, and that's very pretty obvious. We got to know in short. So well, let me jump over to the PPT. Yeah. So LLM. So we have discussed about how this is an objective about ROS LLM, and yeah, system design and methodology. So the proposed framework about ROS LLM integrates an AI agent, which is LLM, with ROS environment. So I've been talking it about a lot. So what are the key components of this? We have an atomic action library, a collection of basic robot actions, reach, grabs, and again place. Each robot have an action talk about implemented with ROS action, ROS service, and Python API. So these are actually stored in a way: name, type of service, type of action, type of code, textual description, and again input and output parameters. For storing this data, this is an actually a good foundation for the robotic skills that actually have been saved in the LLM, so it can describe the way we want. So let's go further with human interactions experiment, which we are going to do. So let me go through the imitation learning model we have talked it about. So yeah, experiment and results. So there was an experiment, three experiments conducted over a year. If we talk about, so yeah, so we have an experiment with the universal robot UR5, which had an to a gripper over here at end effector. If we talk about, let's take this photo as an example for a good understanding. So this is in 6 degree of freedom of URF universal robot. Then we have a coffee machine. So I think the main goal is to actually pick up the coffee, and again make it to the coffee machine and store it to the cabinet. If I'm not wrong, this is the setup we wanted to do. Yeah. So, long horizontal tasks is the name of this experiment over conducted over a year. So you can have a brief read afterwards how it was vented up. And yeah, long horizontal task. The experiment on long horizontal tasks serves to evaluate the system's ability to confront and execute complex multi-step tasks. Example by request, can you make me a coffee? So this is a prompt which we require over here. So this experiment is essential as it represents a real-world scenario where robot needs to perform sequential actions to accomplish a goal requiring a combination of perceptions, manipulations, and decision-making skills. So here we have actually deployed the same as we wanted through the lead programming and not lead programming. So it's as like, can you make me a coffee? This prompt has been taken by LLM. Now robot will actually what here are two main steps. What we can do is like I can train my robot 60 hours as they in the robot is they done, and by through this if I have taught a robot already, I don't need to do anything. I will just say, hey, can you make me a coffee? The robot will do the same actions and actually give me a coffee. So that's how it begins. So in this, the LLM generates a complete autonomous plan from a single prompt. So like how it wants to go, how it will perform the action, and yeah, that's how pretty obvious it is. So yeah, we have a good flow chart over here. So how LLM will discuss it over here. So in this figure 4, we have the robot experimenting like how it will go through the processes, picking up the mug, placing the mug into machine, opening the machine cover, and again opening the cabinet door, picking up and place the bowl. So there is how it works as a human tendency, how we do this flow. So after that, switching on the coffee. So this is how we have an proper example how the robot have actually described on the way. So there are some over there that it has a vision based system over there where it actually covers all of this like picking from a cup to picking up the cup and putting it into the cabinet, and this is how it works. So this is pretty obvious like a easiest example we can talk about. All of this has been described by this the wait a minute, let me show, yeah, okay. So, so like the any wrong screen won't pop up over there like the imitation learning. So yeah, so everything has been described over here. So we can, I think, yeah, over there is a vision based RGB camera over there where they actually describe it, and everything has been planned via action. So yeah, once that is done, there is when we talk about how this sequential six cube task has been completed, like starting picking up a green cube, placing the green cube on top of red cube, and this was another example how they performed, I think, if I'm not wrong. Yeah, it is about uh, via like policy correction via human feedback. The ability to correct policy decisions based on human feedback is crucial to enhance the adaptability and robustness into autonomous systems. In these sections, we present experiment session of generated by LLMs. So yeah, at the beginning, our model is not that much of good enough for describing a robot a whole task. It can describe the whole task but cannot perform with the physical hardware because there is a combination and again perspective problems that robot may face to describe their actions, and that's the reason where we are not that much of good developed onto this, because we need a good a large amount of data set which has been prepared in backend of how we are actually performing it over here. As you know that how LLM works, so that's not an talk about how it is get trained. Similar way it is get trained in the field of robotics, but it takes time about describing coordinates again, a lot of stuff over there. So this is how they have actually described picking up the cube and placing it over here. So boss operation task within Pango. So this is the graph. Updating action library with imitation learning. Yes, this is very important. And enhancing robotic skill set to include a variety of tasks is crucial, especially in household environments where the robotics action may not perform. Okay, this is the second example of where the imitation learning make me a pasta. So this experiment, in short, if we talk about, is being conducted by a non-expert, demonstrating thought news actions. So it's like stay steer, pour, season, wipe. So these are the four actions which was actually covered over here, and system automatically learned about and added how new atomic actions can be performed, and LLM later on use this to perform how sorry LLMs later use these actions to perform a full make pasta routine. So when we talk about this whole actions over there, so let me go through the third experiment. So over there on the paper we have a robot which is actually making over the pasta. It will steer, and again at the end over here we get the end about as adding the seasoning. Like it's a whole procedure that how what an human does with the pasta, so I don't need to go how it made and all. We have been talking about it since long time. So this is how it works. So the task has been specified by LLM action sequence generation. Using the provided task description, the language generates an action sequence for the as same as the flowchart we discovered. And again, as the robot executes the task, the environment is initially by moving the target box, leading to a failure to grab the object. Yeah. Now, in this case, when we have the vision-based system, when this robot is being imitated by giving a extensive learning about to it, it takes a lot of time for to grab with a proper accuracy. Suppose this is something around me and my robot, like the coordinates have been defined properly, and once that is done, the robot may place over here at start, may place over here. The accuracy is not that defined properly. Once we do the imitation learning so properly that the robot can actually grab over this and pick it and place over there. So that's what a main goal is behind the imitation learning. So once that is done, we have remote supervisory control over there. So this is an fourth example taken over there, operated in Europe. So what this shows about is the robot is actually doing kind of action. There is an operator in Europe, and the robot is in Asia. Language through internet. So this is actually a very good for good usage in medical reports. If we talk about like commands like pick the blue box has been told by Europe robot, and it has been placed despite having 2 or 3 seconds of delay because of internet. So through this experiment, it was discovered that remote supervisory control is something which has been actually conducted through worldwide. Like, suppose I'm an operator sitting in Europe and I have my robot doing that action in India. So, for this, it's pretty obvious that it will take a lot of time to understand, to describe it as compared to our development, which is going on till yet. So let me talk about what like it's like just I have given a command. It will publish it over here, and it will receive in Asia's robot. It will do this and perform the action as we wanted. There is a lot of delay, to be honest. Yeah, has been placed over here, but yeah, this experiment also was conducted so that this ROS-LLM technique can understand what is over there. So yeah, this was all about conducting four types of experiment. One, we discussed about long horizon tasks, make me a coffee. Environment was kitchen setup with URF5 robot, and let me go through the yep. So this was all about the did with the real world, and yeah, LLMs generate the complete plan autonomously, and robot successfully executed a 12-step sequence and providing the framework's ability to handle complex multi-stage behavior through languages. So second example was not described that good one. So let me talk about human feedback correction. So at beginning at experiment one, we had a robot which was actually going to make a coffee via a vision system, and again imitation learning. So once that is done, task table top sorting and rearranging using colored box. So it was all about sorting and rearrangement of the cube which we saw over here. Just give me a moment. Yeah, no, this is not what we wanted. Yeah, this was all about how they given the six sequencing six cube of tasks despite over 10 stages, starting picking up a green cube, placing the green cube on top of red cube, picking up orange. So it's like building the box unbox. So what it actually provides is, for us, the result was actually like the human feedback corrected the policy mistakes in real time, improving adaptability and reliability. So this actually tells us that first experiment showed us what actually it does. Through this, we tried to segregate via this other yeah. When we talk about this over here, so there are something attached over this QoS. It's something like, I think, behavior tree, I think. And once that is done, the robot can actually do all over the actions by the human feedback. We need an human feedback. So let's talk about that. How was the session today? So we take feedback and try to improve it as we go through the next session. So that's how it works. So let's go to third experiment. It was all about imitation learning. Non-experts demonstrations taught new actions like steer, pour, season, and wipe. And what I will not go through how it went all. So LLMs later used to perform a full make pasta routine for it, as we described, like make me a coffee instead. So demonstrated continual running and adaptability. Sorry. So this was all about. And fourth one was actually something much crazier. We can talk, and it was actually conducted overseas. So it's like an operator sitting in another country, and over here been deployed. It takes a lot of delays over there. So yeah, so that was all whole over your whole agenda. So this is described that there is a guy who is actually sitting in backstage of something, any in any country, and everything actions actually been performed through the guy who is actually sitting over in Asia. So that's how it went. And you can have the discussions like, the result of our experiment highlights the potential of this approach to simplify the interaction between non-expert users and robotic system through natural language. So this section discusses the implementation of finding the limitations and strength of the current framework and future directions for research. So this research may have anything about good. We can also plan something. You guys can also plan something that we can add something to this the experiment which they conducted over there, and adding more accuracy over this. So this is all about what they did via task 1 and task 2, and what was the time taken by it. So this was all about average time taken after the second implementation of all of these experiments. So this is all about how they went through. So here it is done. Okay, experiment setting set up for the human study. So yep, this was conducted by the Universal Robot 5. So this is what I think they have waited the TLX results for remote supervisory control. So what is the main agenda after when we talk about these experiments? The key findings are enabling natural languaging processing for robot programming. So works with open source LLMs, supports imitation learning and feedback loops. I think imitation learning is much more important on this occasional which they do, and scalable to real world factors. So that's all it was. So when we talk about the discussions and insights from this paper, even without fine tuning, the LLMs can plan a long term for robotics tasks, which we don't generally. The LLMs are required for giving a good prompt, so we do it fine tuning. So here we don't require like doing fine tuning for the LLM. Instead, we actually try to figure out human feedbacks acts as a lightweight correction mechanism over there. And yeah, so that's all about discussions. So one more the fourth example was all about the remote description, which we talk about over here, and a good prompting, which is to be required. I think this is required to be done for, like, LLMs might require fine tuning for good prompt generation, because everything is dependent on over there. And yeah, so what is the future direction for it? The research successfully demonstrates that how an LLM has been connecting with ROS frameworks, connecting it and giving a good prompt and ROS bridges over there. And after that, we have successfully integrated with this paper was actually integration with ROS to I think 20, when 20 was about the seeds, I think. Yep. So the future goals now, they are like now when we talk about the ROS versions which are actually current being used, is all about ROS 2 humble, and again Zazi has been taken too much of good for the development stages. They have conducted it on 20.4, which is not that much of feasible. It's like, and as I discussed, that it is an old paper. So what are the future goals of this integration with ROS2, and again inclusion of vision language model for multimodal reasoning, exploring behavior trees and state machines, and fine tuning open source LLM. This paper is good for them who is actually starting over ROS LLM or something, developing something good into this. So yeah, so this is all about the paper over here. When we talk about discussions related works, the sections revives various approaches that enhances the interaction between robot and human language, focusing on task planning through actions, composing it with integration of model and robotic systems. So yeah, this is where you can find the comparison of related works of how it was been conducted over there with the open source model, the human feedback, the environment. So what were their open source of what they have done through their, everything has been described over this chat, flow chart, and not a flow chart, it's a description via image. So what remote control gave a good experiments they conducted over there. So yeah, this is all about the paper. It was a short paper over there. So this is, they have actually implemented, I think, over the into some challenges, I think. Robotics, humanoid kitchen demonstration, and again humanoid hierarchy. Let's talk about this. Bridging the simulation reality gap is crucial. I think this been conducted into because robot, if I'm not wrong. Yeah. So it's like placing it over here and making it to place. I mean, let's talk about this if we want. Bridging the simulation reality. This has been conducted into high performing embodied intelligence. It's like, yeah, the simulation is much required as compared to like deploying it into actual hardware. So when human learns a new skill such as air hockey, it is common that a tutor mentor will provide feedbacks and suggestion, as I said you. So the learn and intelligence, this feedback augmentation and augment, sorry, this behavior in such a way that it will improve the future performance. And yeah, this is what I have been uh, into the scene as per the robots over there as shown in this figure. So our framework as an interface to enable a human non-expert, as we said about operators, to modify the control policies and robot in order to improve the system performance within the scene and the context robot. So this has been challenged, been played over there. So I will not go that much of deep into that. So this is what the conclusion is. In this section we provide an conclusions as we discussed over here. Limitations, what kind of limitations is there, as we discussed that it has a good limitations through which we need to describe it over here. So yeah, it is important to acknowledge the current limitation presently are explaining rely on action sequences which are not adaptable without human feedback. For example, if the robot must open a door and navigate through, then it might be worthwhile to attempt opening it. Failure, like as I said you, that it does like picking up and placing it away, that requires a lot of a lot of extensive training for it. For example, just as we discussed, this repetition could be achieved with the behavior tree. That's true. We can actually conduct this experiment by doing it manually, but it takes a lot of time for it. So we have recently added an interface that is execute behavior trees generated by the large. So this is something they have done for this, and this feature is already usable in our code base. Future work will investigate the benefits of using behavior trees. I may have shown you some good simulations, but I didn't have a good time over there. Yeah, as I told you, that it has been conducted in Rossman. That doesn't does that of I mean could anything can be conducted over ROS2. I mean the packages and all over it will just change over there, and that's not a that point of we need to discuss that there it's the future work. Anyone could conduct over there and show the good responses to what they want. Actually, you guys can actually contact over them and ask them that how they have moved forward with them. So this was all about the paper. yeah, I think we have came to an end. I hope that it went. I mean, I tried to explain you in simple terms as it has a good code base as well, but they have hidden it, so I was not able to show the simulations which they have actually performed. But yeah, most of this actually I'm familiar with this. So I think this was actually made by the Hyundai's. They have conducted over there. So yeah, Hawaii, sorry, Hawaii, no, Arc Lab, London, UK. So this, yeah, this was a good paper actually I wanted to describe over there. So yes, we are at the end of the session. So if you have any doubts, you can ping me on the chat itself. Till then, let me see some of the stock applications there. There is nothing to talk about. Oh, how it went on in the comments. So, yep, I think we can end up this session. Yep. So all about today we discuss about imitation learning, behavior trees again, how this ROS-LLM framework can be much more implemented and like a generating a prompt, and then all of the actions being conducted by the robot through this behavior using behavior tree and imitation learning. There were four experiments we discussed about. The four experiments was all about long horizon tasks, which robot needs to do it, and successfully they executed a 12-step sequence, providing the framework ability to handle complex multi-stages behavior through language. So it's as simple as that. As I showed you in the picture. Yes, I
Hello,
let me
Ketan.
complete the three as well. So there were three human feedback correction. So in this, human actually gathered the mistakes over there and tried to improve it. And third was all about imitation learning. Make me a pasta, like demonstration, continual learning and adaptability through this process. And one was remote, that it has been shared through another state of country like in Europe, and the actions are being performed in Asia. So that's all about today. So yeah,
Great, Ketan. I was all there on the backstage listening you, and
okay. It went too much of basic, but it's good to know that it has been carried on for the robotics engineer. Yeah.
yeah, so if you guys have any questions, you can ask us in the comments or ask Ketan personally after this session as well. I think tomorrow there will be one more session, and after which we will be able to conclude this series, and we
Yeah.
will go forward with Gen AI-thon and some hackathon stuff which we are planning with you guys. So
So
stay tuned.
one more I would like to add is all about the we are actually bringing a good robotics community in all over Pan India. We are planning for it under the robotics.org, and yep, I mean Nashik is also a good part over here. So we can see a lot of good developments how it is going in India. So for that, stay tuned. Yes, I think we
Great,
can end up the session. Yep. Thank you
fine.
for the time.
So let's wrap up and see you guys afterwards. Can we play some music? Let me see what we can play.
So yeah.